Okay, we should get started. So, in the last class, we looked at a fair number of algorithms which were in the category of informed search algorithms, right. So, the idea of informed search algorithms is that in addition to the search space which is given through this expansion function and goal test and so on, the domain designer additionally gave us a heuristic function, right. This heuristic function h is defined over every node and it estimates what is the cost of the nearest goal, closest goal from this node n. Okay. And then we studied how would we use such a heuristic function if it were given to us, and we discussed the A star algorithm or the general idea of best first search algorithm, which generalizes even breadth first search and uniform cost search. But we extended it to greedy best first search, which uses the heuristic function, A star algorithm which also uses the heuristic function and also has nicer properties. In particular, we can guarantee that A star algorithm is optimal in the tree search version if the heuristic is admissible. And then we went beyond it and we said, oh, the memory problem of the algorithm remains the same, and so can we come up with versions of algorithms which use the heuristic function which do not use that much memory, and we talked about IDA star and depth first search branch and bound. Last but not the least, we said optimality is a luxury. God knows the optimal solution, but these are hard problems, we may not get to the optimal. So, can we come up with some suboptimal algorithm, but which is good enough, at least has an optimality bound, and we talked about weighted A star. So, this is what we did in the last segment, right. And to complete the story, one important question remains: how does the domain designer come up with a heuristic function? In particular, we are interested in admissible heuristics, right. Oh, by the way, there is also a lot of work on coming up with inadmissible heuristics. Now, when we use an inadmissible heuristic, all the bets are off with respect to optimality, right. It is okay. Optimality, as I said, is a luxury. So, all bets are off with respect to optimality. These are suboptimal algorithms again, but sometimes in practice in inadmissible heuristic which is more informed is much better than an admissible heuristic which is less informed. And when I say less informed, I mean that when it estimates the distance to the goal, it is sort of making it sort of far away from it, right. And we also discussed what is the most admissible heuristic possible, most uninformed heuristic possible, and that is what? We discussed this yesterday. What is the most uninformative admissible heuristic? 0. And if my most uninformative admissible heuristic is used, so if 0 is used, what does that my algorithm become? A star becomes uniform cost search, because A star uses Fn is equal to Gn plus Hn. If Hn is 0, A star uses Fn is equal to Gn, which basically means it is uniform cost search. Okay. So, these algorithms are in sort of a composite whole in some sense. They are all extensions of each other, etc. in some ways. Okay. So, the goal for today is to think about how can we come up with admissible heuristics given a new problem. What is it? Is there some theory behind? Is there some mechanism? Is there some thought process that allows us to construct admissible heuristics? Okay. And we will start by discussing first reminding you what is an admissible heuristic. So, an admissible heuristic is an optimistic heuristic. Okay. So, what is an optimistic heuristic? And a heuristic which feels that goal is closer than what it looks like, or I will make more money than I will actually end up going to make, right. So, in other words, if I am in a minimization problem, an admissible heuristic is always a lower bound, and if I am in a maximization problem, my admissible heuristic is always an upper bound. Okay. But we will let us discuss the principles stay, but let us discuss only the minimization problems. So, we are only in the minimization world. So, we go back to our favorite 8 puzzle problem and we ask the question, we have to go from start state to a goal state or the goal state in this case. How can we or can we estimate a heuristic for a node? So, the heuristic's job is to estimate how many steps am I going to take to reach the goal. Now, I would need suggestions from you. Please do not shout, raise your hands. But can you think of a heuristic which is admissible, that is, it is a lower bound, it underestimates the cost that I am going to need to go from, let us say, the start state to the goal state. Any suggestions? Yes, what is your name? Saigwan, yes. Number of misplaced tiles, very good. So, Saigwan suggests that look, lots of tiles are not in their right position. In particular, how many? 7, 2, 4, 5, 6, 8, 3, 1, all of them actually. All the 8 tiles are in the wrong position. And Saigwan says, for this I will at least need 8 steps to go from start to goal. Is he right? Does somebody feel that this is not an admissible heuristic, this is not an underestimate, he is missing something? Nobody? Why is he right? Can you prove that you would at least take these many steps? How would you prove that? Each of the pieces will have to be swapped with the gap. Now, if all the pieces or whatever the pieces are in misplaced positions, they have to come to their correct position. It will at least take one step to come there independently, because you are always swapping with the gap. So, it is not possible that in one step 2 tiles get to the current position. It is just not possible in this game. We are always moving one tile at a time. So, if we are only moving one tile at a time and I have so many misplaced tiles, then I would at least need so many steps. So, is it an admissible heuristic? Yes. Good, not very difficult. So, you can say, oh come on, we do not need a theory behind it, these are easy. Can you come up with a better admissible heuristic, something that is better than Saigwan's heuristic? Better means that it is still admissible, but the cost that you get, the heuristic function that you get is typically bigger, and therefore, it is closer to the actual optimal solution. Yes, what is your name? Ankit. Yes, Ankit. The Manhattan distance between what? What do you mean the Manhattan distance between the final position and the initial position in the puzzle problem? Sum over them for each of the tiles. So, he basically, Ankit says, you look at each tile, you look at the Manhattan distance between the 2 positions and you sum them over each tile, and that will be an admissible heuristic. Now, before we understand this further, let us make sure that we all understand what is Manhattan heuristic or Manhattan distance. Manhattan is, of course, a great, very famous place in New York, right? It is said that if you just stand there in Manhattan, you will hear all languages in the world. Of course, that is not true. There are many, many languages which are not extinct. So, nobody speaks them. By the way, I do not know if you know, we are losing like a few languages every month. The world had 7,000 languages. I do not know how many we have now. Okay? So, we are losing a few languages every month, maybe 2 or something. I have to check the actual numbers, but that is a digression. So, Manhattan has been engineered or has been designed very sort of rectangularly, right. So, you can go, if you have to go from one place to the other place, you will basically go in one direction and then go into the perpendicular direction, go in parallel direction, perpendicular direction, and you can keep doing this until you hit the final destination, and you can do all parallel first and then perpendicular later, all perpendicular first and then parallel later, or in any which way, and you will get to almost the same distance, because these are all equidistant. These are, it is a very well planned part of the neighborhood, right. It is the downtown of New York. By the way, in India also we have some cities which are very well planned. One of them is Chandigarh. So, we could call it Chandigarh distance, but that would not have the same buzz as Manhattan distance. So, we will stick with Manhattan. So, in the case of 7, what is the Manhattan distance? 3, because I need to go 1 right and 2 down. I can go 1 down, 1 right, 1 down, 2 down, 1 right, 2 down, but we will always end up with that distance 3. So, that is the Manhattan distance of 7. So, if we have to compute the heuristic, I will add 3 for 7, I will add 1 for 2, I will add 2 for 4, and I will keep doing this for all the 8 tiles, and I will get a heuristic function. Okay. So, these are the 2 definitions of my heuristics, H1 and H2. H1 is the number of misplaced tiles, H2 is the total Manhattan distance. In this case, H1 is 8, and if you count, H2 will come out to be 18. Now, some questions about H2. Is this an admissible heuristic? Is this an admissible heuristic? Why? Because in this Manhattan world, you are only allowed to make right and bottom or top and left moves, and the shortest path would be, going using the Manhattan distance for that particular node. So, that many steps it will have to take. It is possible it will end up taking more because there is a tile there and I have to clear that gap, and that increases the length, but you can't do less than that, right, and you can prove it formally if you want to. Now, which of these 2 heuristics do you think is a better heuristic, H1 or H2? Why? Realistic is a good word, but let's be. Each term in H1 will be less than or equal to H2, and both of them are admissible. Therefore, overall we can say that H2 will always be greater than or equal to H1, and if H2 is always greater than or equal to H1, that means, and if they are both admissible, that means H2 is quote unquote more informative than H1, and the technical term for this is H2 dominates H1. Like if I have H2, I do not need H1, right. And now, here is a quick example of what happens when I use a heuristic function in comparison with, let us say, iterative deepening search. So, let us say I am in the example where the depth of the goal is 12. There iterative deepening search does solve the problem, but it expands 3 million nodes. That is a lot of nodes to expand. If in comparison you see that A star on H1 requires only 227 nodes, and A star on H2 requires only 73 nodes. Think about, we can't prove anything formally per se, right. In the worst case, things may be exponential, but in practice, A star algorithms are superior by a magnitude, like a large magnitude for most problems if you have a good heuristic. And here H1 is not even that good a heuristic. As you can see, if the goal is at depth 24, iterative deepening search never gets it. A star on H1 does get it after 39,000 expansions, whereas A star on H2 gets it only after 1600 expansions. So, a more informative heuristic more often than not leads to faster running time. However, there is also theory that more informed heuristic can sometimes hurt, but we are not going to again go into that territory. For our practical purposes, more often than not, if you have a better, more informed heuristic, you will probably get to a better solution faster, or same solution faster. Okay, so now these are some examples of admissible heuristics in the context of the 8 puzzle problem, but that does not get us to the general principle. We need to somehow get to some general principle that, given a new problem, allows us to come up with an admissible heuristic quickly. And that general principle is the notion of a relaxed problem. Okay? Let me first describe what a relaxed problem is, and then we will think more about what it means in the context of our 2 heuristics. So, a problem with fewer restrictions is called a relaxed problem. So, think about it, there are some rules of the game. I have to satisfy all the rules of the game to solve my problem, but let us say I take away one rule for you, any rule. I take away one of those rules. Now, the problem that I am left with is called a relaxed problem. It is a relaxation of the original problem. Have any of you heard the word LP relaxation? Some of you may have. You can connect it with that. If you want to solve an ILP, an integer linear program, that means every solution has to be integer. And then you do an LP relaxation, which means that I am not solving an integer linear program only, I am now solving a linear program. That means I have removed the restriction that my variables are integer. Am I removing some of the rules? I am removing the rule that all my values should be integer. Such a problem would be called relaxed problem, and because we solved it using LP, it is called LP relaxation. This concept of relaxation is actually a very important idea whenever you are given a new problem, because a new problem, if it is a challenging enough problem, will have lots of issues, lots of little things that you need to take care of, and initially you will not have intuitions. Even just to do intuition building, you say, okay, let me get rid of some of these rules, let me solve a seemingly simpler problem, let me at least solve that and get an intuition about what is happening in this problem, then I will think about how to solve my original problem. But that is just a strategy that you will use as an intuition, but actually there is an operational application of that in the context of search algorithms. These relaxed problems are actually critically important in computing admissible heuristics. Can somebody guess why? So, the solution of the relaxed problem, any solution? Optimal solution. The optimal solution of the relaxed problem, wait. Can you say something about that with respect to the original problem? It will always be either executable in the original problem or not executable. But if it is not executable, will its cost be less or more? Why less? Every solution, very good, Vishwajit. Every solution of the original problem is a solution of the relaxed problem, because I have only removed some rules, I have not added any new rules. So, any solution of the original problem is a solution in the relaxed problem. If I am solving optimally the relaxed problem, that means I have considered all those original solutions also and all the new solutions which are not even executable. So, the policy that the solution that I am going to get would be better than the optimal solution of the original problem in the relaxed world. Therefore, its cost would always be less or less than equal to the original optimal. In other words, the general principle here is the cost of an optimal solution in the relaxed problem is always, by definition, not by definition, but by our analysis, is going to be an admissible heuristic for the original problem at hand. Now, let us intuitively think about this. What are we relaxing when we say H1? What rule are we relaxing? Wait, let others think also. What are the rules in 8 puzzle? We can only swap with an empty space. Very good. What's your name? Shivam says we can only swap with an empty space. What is another rule? Yeah, that's what. Oh, you can only swap with the neighbors. Ansh, right? So, basically Ansh and Shivam have given us two constraints of the problem. You can only swap with a gap and you can only swap the gap with a neighbor. Good. Now, let us think about this. In H1, what are we relaxing? we can only swap with the neighbors. So, if I allowed my tiles to fly, but I was still only swapping with gaps, what will be the optimal solution here? The first thing I will do is move 4, I will put 4 up, I will have it fly and go into the gap. Now, 4 is in its correct position, it took me one step, and now the 4's original position is open where I can move 2. So, again 2 steps, I have 2 and 4 in the correct place, I have position open, so I can fly 1 and so on and so forth. Now, by relaxing the assumption that I can only swap with the neighbors, I have created a relaxed, and in this relaxed problem the optimal cost is going to be 8, and that is my H1 heuristic, therefore, it is admissible. In the very same way, which constraint am I relaxing when I get to H2? You can only swap with a space. So, that means I can, or I would say not swap, but you can only go into a space. So, swapping means that if I am swapping 7 and 2, then 2 comes left and 7 comes right, that is trickier. But we can say, you can also say that one of my constraints is that there is only one tile at a location. I will have to relax both of those. So, I can say, okay, first I will move 4, so first 4 will go to 6. 6 is also there, that is okay, who cares, 4 and 6 are both sitting there, and then 4 comes left and it gets into its correct position. So, I can move over tiles, right. So, these are the relaxed versions, right. So, as it says in the slide, if the rules of 8 puzzles are relaxed so that a tile can move anywhere, then H1n gives the shortest solution. If the rules are relaxed so the tile can move to any adjacent square in spite of whether there is a tile there or not, then H2 gives me the shortest solution, right. So, therefore, you can think about, so whenever you are given a new problem, you have to analyze what constraints are going on, and based on those constraints you have to say, okay, let me create a relaxed problem, and based on that come up with an admissible heuristic. I will do one other example just for fun, and that is the Hamiltonian cycle problem. Okay. So, first of all, for people who do not know what is Hamiltonian cycle, in a Hamiltonian cycle you have to visit all nodes starting from some node exactly once and come back to the original node. So, for example, you can do it in the order A1, A2, A3, A4, A1 if there are 4 nodes in the graph, or you can do A3, A1, A2, A4, A3, and that will also be a Hamiltonian cycle. So, you are looking for a cycle starting any node which comes back to the same node, visiting each node exactly once. Okay? Everybody with me? And as we know, we can model any problem as search problem, at least these kinds of deterministic single agent problems. So, what will be my node? What will be my state? You have to first think the state space. My state spaces, any suggestion? Set of visited states so far, but set of visited, the set is not necessarily the right, because we need to maintain what is the order, because we have to maintain the cost somehow, and also we have to know which is the end point, right. So, we can say a partial path, right. A partial path could be my state space, and what is my start state? Empty, nothing, and my edge would be expansion, and the expansion would be what? Expand into. So, suppose I currently have a path A1, A2, A3 up to AK in my state space, in my state, then the next child would do what? Visit an unvisited node from AK. Okay. So, I will go to A1 from A1, A2, A3 up to AK to A1, A2, A3 up to AK plus 1, and the AK plus 1 can be one of the many. So, therefore, I will have many children. Okay. So, this is my state space. And now my goal is to figure out an admissible heuristic for the state, let us say A1 up to AK. And in order to do this, and for any such problem that comes along, think about solution constraints. So, what are the constraints on the solution? Visit each node exactly once. What else? Visit all nodes. So, not only visit a node once, but visit all of them. Or you can say that the final solution, the degree of the node should be, degree of each node should be 2, because one will be incoming, one will be outgoing for every node. So, this becomes now my constraints on the solution. And now my only job is to see if I can relax any one of them, and based on that come up with a good heuristic. So, any suggestions on heuristics? What if I get rid of visit all nodes? What can you create? What heuristic can you create? Start from let's do reverse. Start from AK and end with on A1 with any path. With any path using which nodes? Remaining nodes. So, get rid of A1 to AK in the graph, A2 to AK minus 1 in the graph, and then try to compute the shortest path from AK to A1, and that is going to relax visit all nodes constraint. Can you relax any other constraints? So, now there is a nicer admissible heuristic for this problem. Let us see if you can figure this out. Let us say I allow you to relax each node has degree 2 constraint, but you still want to visit all nodes. You have to be louder, please. Sorry. Yeah, good. So, the suggestion is that if degree is more than 2, then third constraint also gets violated. I agree. So, let us violate all of them. Not all of them, both of them, first and the third constraint. Can you think of something that you have studied which does not return something with degree 2, but has some notion of shortest or optimality and something like that? Yes, Sukriti. Minimum spanning tree. So, let us think about what is minimum spanning tree. Minimum spanning tree on the rest of the nodes. So, on the let us say AK to A1 nodes, right, not using A2 to AK minus 1. Now, this minimum spanning tree, would it be an admissible heuristic of the original problem? What is it saying? It is saying visit all nodes? Yes, but should all nodes have degree 2? No. Should all nodes be visited exactly once? Well, there is no notion of, it is a tree, so there is no notion of visiting per se. So, not exactly. So, but will the original solution, the path from AK to A1, will that also be a solution in the minimum spanning tree problem? Will it also be a spanning tree? It is a spanning tree, it is spanning every node. It is not the minimum spanning tree necessarily. So, the minimum spanning tree cost will always be less than the cost of the path from AK to A1. So, that is the intuition of how you come up with admissible heuristics. It is a very general intuition, it is a very valuable intuition. Yes, question. Original solution is a cycle, but for the node, what is the remaining solution? The remaining solution is the path from AK to A1, not using any of the A2 to AK minus 1, but using every other node exactly once. So, we are now interested in estimating the cost of this node to the goal, which is addition of all the other edges, right. So, you have to think in terms of the partial state that you have defined and the heuristic on top of it. But yes, original solution is a cycle, exactly. Good. So, this sort of ends our discussion about domain relaxations. We will stop here.